All right, we have a very limited time, so we're going to go ahead and get started. And I want to welcome all of you brave souls to our Green Building Post Mortem. Let me get back on our slides. You are in the right place to dissect surprisingly common building failures, diagnosing building issues, getting more out of commissioning, and issue prevention. Our session agenda basically mirrors our learning objectives, and we will make every effort to save at least 15 minutes for questions at the end. We do ask again that your questions are questions and not stories, just so we can get as much time together as possible. So let me introduce who we have here today. In this corner, we have George Trapp, commissioning agent extraordinaire with In Posse. He has 30 years of experience in the field. I ran into one of his clients just now, and she also said he is St. George, so you can think of him as St. George or a commissioning agent, whatever you prefer. And we also have Peter Lane Taylor. He is an enclosure specialist with PPSI. He's trained in several high-performance building modeling systems, such as WFI, Therm, and Passive House. And I'm Jennifer Rezeli with Revision Architecture. I'll be your referee. And while I do like to pit George and Peter against each other, the truth is that enclosure and systems are 100% on the same side, and this is a theme that will reoccur throughout our session today. So to kick us off and set a tone for transparency, airing of dirty laundry, whatever you have, I want to quickly share how this session came to be after my firm had a very stressful post-occupancy issue with this lovely LEED Platinum rated building. So it did have its LEED rating, and unfortunately, the client looked like this during the middle of the summer within the first year of occupancy. So the educated thinking at the time was that the mechanical calculations may have been a little too tight. Some chiller coils were replaced. This did not fix the problem. So the second summer, the entire team was sweating like this. And the specifics aren't super important. I will try to quickly summarize what we found out, which is we had a metal deck with open flutes that were not sealed during construction. This rested on a structural support. I don't think my pointer works, but you can see a red arrow pointing to that. It was that wall happened to be very unfortunately located next to an unconditioned trash room with an open louver, plenum above, sucking air at high velocity and crashing our system. So it was this tiny, $10 fix that took several years to suss out. And the commissioning agent who finally found this little leak said, you'd be surprised how often I see this problem. Yeah, we were surprised, and it got me wondering what else commissioning agents are seeing that we can learn from, and how we could have made better use of that owner's commissioning agent and found the problem sooner. This is sort of an awkward setup. We may be up and down or just going back and forth here. We're going to try and do this as much as a question and answer as we can. But my first question to you guys is this just me? How common is underperformance in green buildings, would you say, in your opinion, in a nutshell?
I'd say 99% of the buildings I go in underperform.
As compared to energy model, or just in terms of?
The energy model, and also in terms of the owner's requirements.
Well, I wish we could say in front of all of you that on the enclosure side, we don't see a lot of issues. I'd say they're persistent, if not pervasive, on every project. And high-performance buildings have to be airtight, thermally tight, vapor tight, and you can't have a durable green building if you don't have a tight enclosure. So persistently, unfortunately.
Okay, well, Lawrence Berkeley National Lab backs this up. They sampled 122 buildings, and they found over 10,000 issues on those buildings. They did acknowledge that they were not looking very well at enclosure, and so this was really just on the system side. You added enclosure issues, and we're into the hundreds of issues on every building. And George, I know you went and did a survey of your own buildings. You looked at 10 recent projects and you surfaced 1,000 issues, which is really right in line with that Lawrence Berkeley study. So I'm realizing now as I'm saying this out loud, this is kind of sounding like a downer. We have like hundreds of issues on all these buildings. But we are going to talk about solutions and prevention as well. George, the highest count from the issue logs that you went through was installation. So I'm going to ask you to take us through some of the kinds of things you typically see on projects, and then we're going to talk about what we can do to prevent that.
Yes, as far as the most number, as you can see, on our installation effects, and that's where a contractor has done something that didn't meet up with the design intent, or something happened in the field that created these issues. So we just put up a couple shots here of what we see a lot. Photosensors shaded. We also see sensors, and when somebody walks down the hallway, the office lights that are empty go on, and instances with the electrical side. We also see things that are wired incorrectly and they operate all the time. Exhaust fans that are just hardwired and operate 24/7, 365. Then the next picture, you're looking at a hot water valve that cannot be shut off unless you're going to take that handle or bend it to get it out of the way. So we also, and that's part of like the serviceability that we look at when we're commissioning jobs, trying to see that it's serviceable equipment and that you can isolate things when you need to. Duct leakage, or sometimes we see ducts that aren't even connected to anything. They just blow off into the ceiling. They're supposed to be connected to a VAV box, and also they leak where the joints come off of the main duct. And then we had problems where we've seen that the protection, which is nice because the contractor will protect the ductwork during construction to stop it from becoming dirty when startup comes, and then they forget to take that plastic off. And then they operate the system, and we're not getting any air into the space, and we end up, in this case, we pulled the floor up because it was an underfloor system and found that the duct protection was still in place. So the dampers are running, and the contractor says, oh yeah, that system's working, watch the damper operate. Well, wasn't operating too, and the system was balanced, by the way, already.
Well, let me interrupt for a second. So George, I mean, are these isolated, like, oh, I had a horror story on this job, or would you say these are typical things that you see?
These are typical things that I see all the time. And of those 1,050 that I looked at, there was almost 200 of them were installation issues, and I took the top 650 out of that. So you're looking at almost a third of the issues that come up are faulty installation in the field. Not to pick on install contractors, but that happens to be the biggest one that's in there. And then we've also had fans running backwards. Sometimes we'll see linkages that are never even hooked up on valves and dampers, and that's pretty much what we got on that one. There's a lot of other ones, I just picked some of the top ones. And then another thing that we see common in the field, we'll see a contractor who decides that why buy that big expensive elbow that's long radius when I can get short ones for a quarter of the price. And he goes and he installs all these different duct connections that are not what was specified or what was in the design intent. And for an example, that a rectangular elbow would be like you measure resistance of duct by equivalent feet. So how long is the duct? An elbow would be an equivalent length of straight duct. So a rectangular elbow would be around 65 feet of duct. I just pulled a few examples off the SMACNA charts. And if you put turning vanes in there, it goes down to 14 feet of duct. So you can imagine on a large duct system, these wrong selected fittings create horrendous problems down the line. You end up with an engineer designing a fan that may or may not be able to overcome that much resistance, and fans are being more and more right-sized to make what was designed, not to make up for all the mistakes that are going to happen out in the field.
So I guess, George, I mean, field changes happen everywhere on every kind of project, obviously not just on green projects, but could you again hit home why this is so relevant if you have a green project, why this problem is magnified?
Yeah, in a green project, we're trying to size the equipment to meet the need, not to oversize. In years gone by, I'm sure everybody who's been in existing buildings realizes how big equipment got the end just to be sure. So the engineer put in 10%, and the contractor put on 20%, and now, hey, let's make it twice as big as it has to be. That's how we're now in the position we are today. So now the pendulum swung the other way, and we're saying, just give me enough fan to push the amount of air out that I'm talking about, put a little dirty, just to overcome when the coil gets, when the filters get a little dirty, and that's it. And that's all we're going to do. Same thing with pumps and valves. So you put a bunch of fittings in there that wasn't in that design intent, looked at as have a pump that may be that is undersized, when in actuality it's sized correctly if the design was installed.
So George pretty much keyed me up perfectly for the form slides you're looking at now. The high-performance HVAC systems that George is talking about is predicated precisely on a building enclosure system that's also designed that. So for those of you who aren't 100% clear what you're looking at, the slide on the left is actually a demonstration mock-up of an air-water dryer system that was done for an owner. So this is a trained technician, right, in the employed, good conditions. On the right is the week half of what the owner actually got in the field. We call this, contractors call it origami from hell. It's taking a bunch of membranes and self-adhered things and trying to stack them up against one another. And I think the moral for all the architects and designers and the builders is that building enclosure materials typically don't fail in the middle of the field of the wall or the middle of a roof. It's where all these things come together, and tiny areas with tiny seals and gaskets and tapes. So it's really a matter of setting on board expectations and getting the entire design team on. I think we really feel that it's about heightened awareness. Designers have to be communicating with people in the field. People in the field, if they have field changes, as George said, have to communicate that back upstream. We ironically always come back to painting, because it's something that everybody in the world understands, and pretty much everything in the building preparation is fundamentally like painting. It's about surface proper foremost. It's about proper installation, thickness, proper curing. So these seems like somewhat basic sounding, but it's something that design teams have to constantly keep to the entire team all the way through, even down to the mechanics of the field.
With you. So I think in talking both about this previously, the recommendation had really been field crew, getting as close as you can to those field crews clear and having the design intent clear. So forget the drawings for a minute. Here's what we're trying to do with resistance. If you're talking to the duct crew, we're trying to have minimal resistance. Here's why the elbow sizes are so important. So again, it is that change in awareness, hopefully to reduce field changes. Our field changes, maybe they'll be closer to the drawing. Similarly would typically be in this kind of situation.
Correct.
Similarly on the enclosure, we're trying to get a continuous membrane. And so communicating that to all of the field crews, here's the goal, stop what we're trying to see. If you see a gap in there, stop immediately. You need to call attention to it. That's our design intent. There's a continuous enclosure. So there's the drawings and then intent. Both of you, and the intent is not really, I mean, what I'm hearing from both of you, not really getting to the field crews very well.
Correct.
When we do our ticket commissioning meetings, a lot of times I look at the user attendant table, and it's always the superintendents, the owners. It's never the foreman or the field crew that ends up in those meetings. So we end up preaching the design intent to the wrong audience. And I think that's one of the things that we need to do. We need to get off people into these commissioning kick meetings so they understand the nuances of working on a high-performance building as opposed to a typical constructed building that they do. So I think it's important that we get that down.
So the next big issue on your count, George, was sequence. And both something Peter and George mentioned this numerous times. It meant very different in each of you. So George, let's start with you and talk about what you mean when you're talking about sequence and the issues you're finding.
Yeah, to me, sequence is related to how components and systems operate together to provide the design intent. So one thing happens to another, and they work their way along the line. You could have dampers that are running for heating and cooling, and you can end up where they should properly sequence so that you're getting cooling when the outside air is capable of doing that. Instead, you end up with dampers that are opposing each other and not bringing in proper temperature air that can take advantage of some of the design criteria that were put out in the spec. And a lot of things we see will be valves that operate simultaneously instead of after each other. You can actually, I've seen instances where a cooling valve is open and running and the heat up after is trying to reheat the air back up, cooled down. You'll see dampers that end up open and heating. Cold weather outside, they'll drive the heat on when they don't need to be. There's warm enough return air to blend the in. So it's important that the sequence who's going to run the sequence of operation for the control. I wanted to relate something that I see happening more and more often coming across my desk. We'll have the control engineer intend a sequence of operation that he then produced in the field. Then the controls contractor, when he does his submittals, he copies that exact document and sends it back in as a submittal. So the engineer looking to approve the submittal is reading his own draft to how something goes. And that's exactly what happens these days. It's kind of new, but I'm sure other people out there are seeing the same thing. The problem with that, I it right back to them what they put out. The problem with that is the controls guy, he doesn't want to have his stuff rejected. So he gives you back a thing to reject your own work. You know, that's one that he's trying to do. He doesn't want to put any more time than he has to into it. And the problem now becomes, how do I get the right sequence that's going to go into the field? Because here's what's going to happen. You approve that submittal, and then in the field, the controls contractor, he does exactly what he wants to do on every other job that he's ever done. He's got a box full of controls programs that he's going to run, and that's what he puts in to the system. And now you go out there to commission, and you wrote your commissioning functional testing docs against that sequence of operation, only to find out and that looks nothing like what's really going on. It becomes a bit worth at the time of commissioning, trying to get to the bottom of just what it is that. So at this point in time, I suggest that if you get something exactly like what you wrote, accept it and put on there that you are not until you see what it is. The control engineer has to write a specification that Honeywell, the bid list, Siemens, anybody can on this has the opportunity to bid against. He can't write it specific to every customer. So we got to stop that from happening. That's one of the common and problem areas that we have in commissioning.
And sequence is also enclosure, so Peter, but very different situation here.
Slides. It was actually hard for us to come up with a sequence of slides to best use for this because there's hundreds of opportunities. So a lot of you there probably don't know exactly what you're looking at, which I think is part of the issue here, because when you're in design sequence, yes, it's very hard to anticipate. Design is really no surprise why builders and architects and teams can't anticipate in advance that they're going to get a situation like this, but just so everyone knows what you're looking at in the back right, you probably won't be able to see, but this is a precast wall system here. There was a curtain wall window mullion. That was a transition membrane connecting from the back of the precast to the window mullion. And this was intended to receive a spray foam air barrier system on the back side of the precast. What you can see in the far picture on the right there, that's a 1-inch gap, where what had happened when the spray foam was installed up against that transition membrane, it literally pulled it right off of the window mullion. 1 inch. So you probably had about 600 linear feet of gap like this on every floor of an 11-story new business school. So going back to what George and I keep talking about, that's the equivalent of having 11 windows open year-round from a conditioning standpoint. So what was interesting about this after the fact in diagnosing exterior sealant, what we determined is that there was supposed to be an exterior sealant on the face of the precast of the window mullion, which would have protected that transition membrane. Over the course of 2 or 3 months, it kept raining, wind-driven rain hit the backside of that transition membrane, in the adhesion. So by the time the spray foam installed the tank and it played that little lift of spray foam there, when it shrank, it pulled away the transition membrane, it pulled it right away from the window. So this was something after the fact that was very disruptive, very costly, held up the actual close-in of the structure, but could have been very easily in the car if everyone had sat down at a pre-coordination meeting with the contractor, general contractor, and actually realized that if they adjusted the sequence of these operations, they could have done it back without actually having to go back and do it after the fact. So really the moral of this is that these are good details. I'm sure everyone looking at these in the room, probably does these all on the air control and good 2D details. You see the air control layer, you see the water control layer, vapor control layer. You build from these. So think about sequence. You've got 4 or 5 different trades constructing a detail like this. You've got a carpenter, interior drywall, glazing contractor, sealing contractor. So we're talking. These are also fairly small areas too. So about 5 square feet coming together. Think about 3D. So this is a simple cut through a wall section. What happens when you hit an inside and outside corner? What happens when you hit a water table or a pier in the structure or some geometry like that? So I think as George said with respect to mechanical systems, people think in components. Most trades are very myopic, so they're just looking at their glass or their sealant or their air control layer. What we really have to do is start understanding these things as a full assembly. Air tightness, water tightness, vapor tightness, these are things that have to be continuous throughout the building. I think you've said it twice already. We keep coming back to the word continuity, that all these things actually have to tie together. And not to compliment sequence beam moderator, but this is actually a window from see these types of details. It's fabulous. The more we see, the less you see all the same in the field, and you can see here layers that you do that 2D detail, but it's actually progressive. So you can see each layer going in one over the other. You can see the openings are actually, you can see the terminations. You can see how things actually fly. Think about this from an so as George was saying previously, story. It tells them why it's actually taking off this job. That tells a story that when it's in who they're going to be following. So there's some sequence in a drawing like this that, in our experience, does a huge amount to avoid that type of field, and that's out of whack. And this again, we have to. We always show you 100 different pictures just to come up with this. See this duct tape of the construction world. So I don't remember exactly what was happening here. This was probably a sill pin not installed with the wind dam. So from the top of that sill to the underside of the window, so they just put a 1-inch gap running around it. Would be horrified. I think everybody in this room would probably be by sealants. Their buildings are literally duct taped together because of bad coordination and sequence. Let's talk real quick about mock-ups. Quick show of hands, how many people in the room do mock-ups regularly? We sometimes get so pushback, long lead times, they're disruptive. If you have these are really too good, you don't want to just buy one. These are good examples that we want to show you how mock-ups can go in a way to avoid these type of collisions on sequencing. This mock-up too, keep in mind we're not just talking about the air barrier, not just talking about the insulation. Sure. So the structural backup here is everything in the wall assembly. So whether it's block or stud wall, the exterior sheathing, air water control layers, masonry ties, insulation systems, cladding, glazing, sealants, on and on. What you can see here in that picture, right, and I think this one is particularly telling. So you're wrapping into the rough opener. That's your continuous air barrier opening. That's 2 inches of insulation, air space in your masonry veneer. Notice that brick tie down there? So in this mock-up, this was supposed to have continuous 2 inches of insulation on was designed on the wall. They chose a brick tie that was pushed off the back wall. So all of the insulation was back up wall, half an inch. So if you think about that thermally, that's effectively an uninsulated wall. You have convective airflow behind that insulation. The insulation is just sitting in the cavity. The simple adjustment was to change that interface of the insulation, change it to one that was actually adjustable on the outer insulation sheathing board. You could lay flush up against that sheathing. What we discovered, that was a cladding rail. Discovered in this mock-up is that water draining down the air water barrier would literally hit that cladding rail, sit there like a gutter, drain right back along. We found 100 of these structures. So again, we could have mock-ups, everybody sitting with a good sense of how just by sitting around, you can determine these very small construction changes that can happen in the field before this becomes permanent work on a building that's 40,000 feet, and you can minimize these problems from happening in the first. Specifying documentation standpoint, a work detail submittal is fabulous. As the detail showed you from Jenn's firm, this could be graphical in terms of, it could also be all the layers that are going in together. This could be in Division 7. That incorporates all of those things within expansion joints, below grade waterproofing, flashing, expansion. All those things, again, have to tie together for a continuous building enclosure system. So look at those potential sequencing things, get them documented up front. The thing that Jenn and I have kept coming back to in the discussion is it gets people to communicate. So as an architect for an air barrier, set shop drawings for your glazing, a set of shop drawings, looking at 3 different documents. They all actually connect with one another, but you're looking at documents, shop which have been coordinated with one another. So for glazing that actually show sealant joints are a wonderful thing. Shop drawings for air barriers that show glazing are a wonderful thing. Now those trades actually have to communicate on a project. We've seen shop drawings that started completely documented. Then when the 3 of them had to get into a room to act together, were fabulous. The drawings that the architect actually got were showed sequence, they showed the interface of materials, they showed where materials had to tie together. So there's an enormous amount of collision that can actually be avoided just through the shop drawing process in and of itself. Just funny, we wanted to touch on this. It's we see come up on every job. So it's that final area, right? So maybe it's a couple windows left open. They were outrigger drywall, other interior materials. Maybe it was a crane or a mast climber where they left up. These are long gone. Typically do the building enclosure materials. Your glaze job, your air water barrier contractor, they're off to the next. So you typically have laborers on site who are now responsible for stitching up the air seal in that enclosure. So this could be a penetration, water bricked up right around it. They pull a crane outrigger off, you've around it. Don't actually tie that in and make it continuous together. So address these areas in terms of the overall building enclosure. As Jenn was noting before, we're talking holes, quarter of an inch, half an inch, 3/16 of an inch. A hole is a hole, as far as waterproofing, air tightness, vapor tightness are concerned. So close in these final areas that you have to just take. You consider these properly. You don't want to have these relying on duct sealant, as we were joking about before. A couple of things we want to touch on too, just in terms of some things we see really in the design community recently, which I think really takes a lot. In Europe, they have a out of the whole process. Have a trade in the whole EAs. So these are basically people that own the insulation, framing, the airtight system, cladding components. So they own the wall back to front. So instead of having 4 or 5 different contractors trying to make all these systems that are going to function together, assess their compatibility, whether responsible for a source accountable entity who's for all of the tightness, water tightness, vapor tightness, and thermal tightness of that assembly. So from a general contractor standpoint, some coordination, one person have to coordinate in among themselves. Not for responsibility standpoint, if that building enclosure is performing, one person on the hook, and potentially a single source warrant. So we're starting to see a lot more of that in particular markets in the United States, and certainly an interest in modularization of building enclosures where the entire building enclosure is built off-site in a controlled factory and then delivered out to the field to be able to put together on-site. But really the moral of the story is continuity. We can't hammer that home enough. Continuity of trades is just as important as continuity of material. The more we can defragment all the people that are trying to put these together, and much more likely to have a complete and air and vapor tight enclosure.
Right, so we're going to flip back to systems and talk about the next issue count, which is a pretty technical issue, I'll be honest, that I didn't fully appreciate until putting together the session with George, and that is calibration. So off on George has explained, sometimes your sensors are off day one, always sometimes they go awry over time. That's the part that confused me, like, why did they just stop working all of a sudden? They were just working. So George has straightened me out on that, and I'm asking him to illuminate you in terms of calibration, why this is so important, and what's happening in your buildings.
I'll do the best I can. Sensors and calibrations are very complicated, almost magical kind of. So first I'd like to describe the different types of sensors that we have out there. And the first one is temperature controls. Everybody's pretty familiar with them because that's what control the temperature in your space with. Also thermostat you have put on the wall. Equalizer operation or air controls, economy operation. So you get free cooling when the outside air drops low enough that you can bring in outside air to do, and you can cut your chillers off or give them a little bit of a rest. Air temperature. You have boilers that start up when the outside air goes. Same thing would need to get heating in the building. Sensor. So anytime you have a sensor that's a temperature sensor controlling a piece of equipment, important you turn on or off that piece of equipment is very important for you to save money and to economize on what utility costs are going to be. Turning that thing on, it's 50. A chiller on when it thinks 5 outside and it's 45 outside, not a good thing. So the calibration of these control duct, what we want to address here. You have also sensors, which are usually temperature or humidity sensors, put in ductwork. They're operating a cooling valve, a heating valve. They could be operating a steam humidifier. They could be operating a reheat coil. So you're just running your heating and then opening up your cooling at the same time to try to counteract it. Room sensors we talked about, they run your reheats, they determine how much airflow is going to go into your space. When you are running too high of airflow, you have a fan back there that's ramping up high to overcome your deficiency. The thing that I mentioned was drift, what they call in the controls community, get out of that, and it can get you in as much trouble as trying to get out of that. What happened? So is you say, what could possibly go wrong between a calibrated control system to get that out of calibration? When you think about the fact that you have a sensor that's in a controlled environment, harsh, sometimes harsh, that could get times, it could get overheated sometimes. One also have a transducer which takes form of energy like pressure or temperature, converts it into a different type of a signal. So you have that on your diaphragm pushing on, and it's going across the resistor. Things wear. Then you have braid across each other. Then signal conditioning, where you're taking a analog signal coming in and converting it over to a different type of signal. And then you have the software that processes the whole thing and then puts up the number that you see in front of you. So there's going on behind the scenes when you look at your building system and you see that the outside air temperature is 30 degrees outside. A lot went in dry, bringing them 3 and at 5 up in front of your eyes to see. And a lot can go wrong. So it was a lot of guys say, oh, that came from the factory, and it was calibrated at the factory. And then it rode a train, then a UPS truck, and then it got in the back of the guy's service truck. Then the duct thrown into the job box, got set up on top of the duct, got knocked down on the floor half a dozen times, then got pulled out, stuck into the duct, put the wires on it. It's ready to go. And we find that when we're commissioning that these sensors, I find temperature sensors 4 or 5 degrees off. And you end up having to put offset in there to get it back, because what you don't want to do in a high-performance building is operate above or below lines that you've set in your design. That's just going to look, it's going to cost money. And then, so you have a bunch of different kinds of sensors. You ought to have them looked at once a year. Have your control contractor come in and take a look and do that. And as a commissioning agent in a high-performance building, I would like to see a test hole put that temperature sensor. So when the guy comes in there with a hole in it and balancers plug in there, just feeding the calibrated instrument right next to it. Now you're reading that every time from the same place, and if your operators are doing your own calibration, they're reading it with the same instrument. So at the time, you collect data that is the same data location every time. I suggest that in pretty much every week. Somebody asked me about how do calibrate. I walk into a job and I go into it's a big classroom, like the size of a classroom like this. And I walk into the mechanical equipment on the 8th floor. There's a door in the duct that you walk to get to the outside air. All the units along the line are running 100% outside air, and it's 20 degrees outside. All days. We were testing this equipment over the holidays a couple years ago at a local university, and then so I'm saying, wow, 20 degrees outside, the air's coming in. I wonder what's going on with that. I come to find out that they have CO2 sensors in these rooms, and they have a demand control ventilation system that opens up a little more outside air levels down to try to get the CO2 levels down. These sensors are 100 parts per million. So these sensors are far off of calibration. They think it's 2,500 parts per million in this auditorium. It was actually a teaching classroom. And that was pushing the demand open. Ventilation control open until degrees. All the dampers were wide open, 20 degrees outside. And the steam heat is blasting away, trying to heat the air back up to keep it cool conditioned. And then it was overheating, and the cooling coil was running to cool it back down to 55 degrees to put it. It was like, this is unbelievable. You would think that how can this be? But that's the God's honest truth, what you run into out there.
Like every day.
Every job I'm going on, I'm seeing it.
Great. And then we just wanted to bet quickly on one particular design issue is very relevant in green buildings and actually is not accounted for in energy modeling, which again magnifies the
So George and I have had some very lively discussions about this, and going back to what George was just saying about really the precision nature of 8x20 systems in sustainable buildings, not amping it up 100% smart, coding it, but really trying to hit your bench. George assumes a lot of very lively debates about, well, what assumptions do you make in a building enclosure? Do you assume it's super insulated, completely airtight? So we wanted, of all the design issues, we thought we'd pick thermal bridging, because obviously in sustainable buildings, LEED buildings, we're shooting for the highest possible thermal value, exceeding code sometimes, and certainly trying to make insulation continuous. So I thought these pictures were very telling, particularly the one on the top left, where you can see this was an infrared thermography scan. But as designers out there, you design a building, you assume you have R19 insulation, R28 insulation. It might say that on the data sheet, it might look that way in a simple model. You go out and look how the building's constructed, that's what you're actually seeing. So the amount of thermal bridging that we see on jobs is absolutely enormous at parapets, slab edges, balconies, you name it as far as from a design standpoint. So my question always back to George was, how do you take all the sensors that are so precisely calibrated with so little margin for error and make them work when you've got this amount of variability happening on a project? So I guess really the moral of this is twofold. One, from an energy loss standpoint, thermal bridging is, I think, highly, highly underestimated in a good performing building enclosure. That picture in the bottom center, that's a moisture issue. So keep in mind too, bridging is not just a conditioned space issue, it's not an energy issue. Those were trusses going through to a cold portion of the wall, basically big cooling fins. The warm, moist air on the inside of that structure was hitting those cold trusses, getting the drywall wet, promoting mold. So when we talk about thermal bridging, really keep in mind, this is not just an energy issue, this is a moisture and potential condensation issue inside of that structure. These are some really basic therm models that have been done, and what you're seeing here, so that actually is a 6-inch stud wall with exterior gypsum sheathing, and that's a Z-girth that carries a metal panel. So in an ideal therm model, you want to see those isotherms, exactly vertical. You don't want to see a lot of temperature fluctuation. You can see right at that continuous metal component, they start to widen right up, and that's where you're losing a lot of that radiant heat. The real moral of these images, as pretty as they are to look at, it's really in the numbers, so I know there's a lot of information on these slides. Just go to the far right column, which I think is really the salient numbers. These aren't thermal hits of 8%, 5%, 6%. These are 40, 50% that you're getting at any type of thermal bridge like this. So going back to that original slide, the Z-girth, that was only an 18-inch high section of wall area. What if you have metal panels going up 5 stories with Z-girths every 18 inches on center? Start in aggregate to think about how much actual thermal loss is occurring at these locations, and then pity people like George, who actually have to take all those sensors and figure out how to calibrate a building properly when you actually don't have the amount of certainty that you need. So I guess really one of the big morals of this, and it goes back to Jenn's original story, a lot of building enclosure materials get buried. Other than curtain wall, it's not really sexy stuff, right? It's membranes, things in a buckets, tapes, so it doesn't get a lot of attention from designers. But having to do what Jenn's firm had to do after the fact, from a cost and a time standpoint to diagnose is something, at least we want you to come away here really trying to avoid. So really the best thing that we can encourage you to do is really try to find some of these things out before the fact, before you close in. So Jenn's building had a problem with about, 12 linear feet of fluted deck area. That could be missed on any size job, let alone a large one. So really the question back to you is, how do you identify these things beforehand, before you have to go through the exercise of doing them after the fact, where they're far more costly? So some of the things we've discussed, mock-ups are already very critical. Review the shop drawings, look at sequencing submittals, get a narrative out there. But there are some performance validation tools that you can use as designers and builders that are extremely effective in terms of simple things like airtightness. Army Corps of Engineer, Lead for Homes, Passive House, all have a required air tightness limit that you have to meet before close-in, before occupancy. Without going into the numbers, these are pretty tight numbers. So, from a commercial standpoint, this is basically a commercial blower door test. What's important for everyone to understand here is this isn't just testing one barrier. This is the roof in, the glazing on, sealant joints in. This is the entire airtight assembly, not just a single component of it. So stating the obvious, you better have access to it. So if you find that you're failing these air tightness tests over and over again, if you have brick up over your airtight layer, you've got a problem. You can't get to it. So when you think about doing air tightness testing, whether it's required or whether it's something you do voluntarily on a job, coordinate with the general contractor, make sure you still have access to these materials. If you diagnose a potential underperformance issue and you can't fix it, you go right back to sealant, spray foam, and duct tape. So try and make sure you do these things before the fact and make sure that everybody in the team's on board. These are a couple other really good ones that people can do on jobs. And again, these can be done on standalone mock-ups that are then repeated on the actual structure itself. These can be done on mock-ups that are actually done on the building. But air and water infiltration tests at 50 and 90% construction. Select thermographic scans at locations where you know you're going to have substantial thermal bridging. Sealant pull tests at critical sealant joints. Precast is a great example. Precast is not a redundant barrier wall. It's effectively relying on sealant joints for its air and water tightness. Maybe a great place to do some sealant tests to make sure that those are going to be durable over time. And then smoke and bubble tests as well. But really the message we're trying to give you here is the cost of doing this after the fact, when you have an issue like Jenn had or the issues that George are discussing. Layers are buried. The mechanicals are buried. The air tightness layer is buried, permanent, already installed and constructed, and having to diagnose those materials after the time is incredible. The fix that's actually going to work and be durable as well is costly, affects reputation, is disruptive. So things that you can do to performance validate after the fact. Army strong recommendations, whether required by lead or required by we've heard them up front. Simple things like air tightness tests number enclosure, 25 to 30 cents a square foot of building enclosure. So that's not an enormous amount of money when you're talking about a building enclosure that could cost hundreds of thousands of dollars with systems and claddings in front. Maybe that $25,000 spent up front is things now before you well invested money in terms of finding the things you actually have to do them after the fact.
I mean, I was blown away to learn the Army Corps of Engineers requires this, right? So they're the largest volume before builder in the U.S., and this is the requirement they have closed office. So, you know, I don't. This is one advice, but really, this instance, people think they're really setting a standard that green building community should get serious about. So we are going to now enter the speed portion of our presentation. We're going to do some selective demolition here, and we're entering the commissioning section of it. The main point we wanted to make here is that a lot of the issues we're talking about today, things like duct leakage to the $3.5 billion a year, or dampers not working, $500 million a year, are things that could be caught by commissioning, by performance classification. They are two disciplines that are misunderstood and often cheaped out on, frankly. So I'm just going to simplify and say take them seriously. I'm going to skip some of the primer on it. We have been talking about systems commissioning. Before commissioning is part of that. It is coming as part of LEED 4. I think people are going to be seeing more and more of commissioning as part of the green building process. We did want to leave a little bit of time for George to talk about some of the commissioning pitfalls he's seeing, and then I think we'll just move right into Q&A.
I know a lot of times now we're finding that where the contractor is asked to perform the pre-functional testing because it's less expensive than having the commissioning agent perform it. And I happen to disagree with that because I think the end result of having that done by the contractor results in when you go to do the functional testing, you end up in a lot of trouble trying to figure out why can't I get this equipment to perform according to the way it was designed. And you end up doing forensic commissioning, as somebody in the audience, as an owner, knows what that's all about. And so we've had problems where we've had pipes buried in walls that were hooked to the wrong spot, past balancing, and they passed. And yet when we went to commission it, we couldn't get the cooling coil across. We find it piped across the chiller, not across the pumps.
And this was just an excerpt that we handled from a pre-functional checklist. So, you know, again, my understanding is, George, oftentimes you will issue as the commissioning agent the pre to save my checklist to the contractor. The owner will have let or fill it out. So questions like, what is it? Is the air-cooled condenser properly mounted? Is the one saying, yeah, it's properly mounted. Later get, as George is pointing out, a lot of the things on here area commission to see. So this is a big problem with the project process, and you know, in the course of putting this all together, I talked to multiple commissioning agents. They all brought this up as a big issue.
It doesn't
don't do it.
And it doesn't save money in the long run to the owner even. So some of the other pitfalls I find, there's customers who ask me to write their OPR after the construction documents were done. I don't see that as being bad points for anybody except for to try to make the lead for functional having the OPR. To complete the functional test before the units have been balanced. Run up and then schedule all the time. And I see why. And then the owner's pushing you to, just start testing it now. We haven't even balanced it yet. And then we keep into the things we're finding during commissioning, and the result that you're asked to sign off on provider will pick these up later. Well, later is too late. By the time that happens, the contractor's off. You're not going to get him back to do anything for you. But there are some of the pitfalls that
And the last one was actually for just from my experience in the management of commissioning agencies, confused a big gap. So a lot of confusion issues around that. Oftentimes the architect issues RFP, the owner holds the contract, the construction manager is responsible for keeping abreast of the schedule, which apparently they never do, so they're not out to the job site at the right time. So just some quick suggestions there. We've got to get clear communication structures in those commissioning proposals, really look at that and have the conversation with everybody on the team. Again, simple, make commissioning a standing item at job meetings. Seems dumb, but it's not really being done. And then educating the owner on the commissioning agent role, value, and expectation. And if you're communicating the value as you need them for lead, you don't really understand the value and you're not communicating it well. So it's really taking the time to get educated on that. I'm going to skip ahead. Real costs and savings is, Lawrence Berkeley argues commissioning being the single most cost-effective strategy for reducing energy. So again, this is just something to take seriously. And this is not just insurance, which it has a function of, but it is real return on investment year in terms of the payback that you're looking at. 1.1 years, it's 4.2 years for a new building. It's kind of beautiful how terrific these numbers are and how underutilized commissioning is. This is, I will leave you with this image. George had me and Peter cracking up, and how many times simultaneously as he was explaining how many times he's overriding behind the curtain, manually doing overrides during the plaque ceremony to make the building comfortable. So doesn't that look like George? He got a haircut this morning for you people, but yesterday we are definitely looked like the Wizard of Oz. Desperate and practice this situation. I hope we had things here. George and Peter are fun, aren't they? So thank you to them, and thank you to the other folks we tossed in for you on putting this together to cross-check some of this information. Everybody was great. We'll take your questions. And remember, questions, not stories. Go ahead.
Right now, it seems like the industry standard for designers isn't to do a lot of the things that you developer own. And so I find I work for a developer owner, and often we find ourselves struggling to consult and get the design consultants to sort of step out of the standards box, whereas they paste in the same things they've used over and over again, and sort of, I don't know if an AIA deals with that, or, but how do you this sort of push your designers to embrace some of this stuff, because they're not, driving the boat. It's really the owner who's sort of pushing them to do some of these things, or the contractor on the back end says, well, you didn't tell me to do it that way.
I just feel like you have the wrong design. Franchise there, but we often don't. Frankly, there's a first truth is we feel like there's a first design problem across the board that just the designer's perspective is everything is pinched, right? They want you to pull out a drawer number 3 because they don't want to pay you to think about it, and so I feel like that's the problem. Not that we want to be, no pushing needed. It's more just the first cost allocation and where it needs to be, whether it is performance verification, cost products, commissioning, those are all a first problem. Developer.
I think the one thing I would add to that is it goes with money. A lot of the things we're talking about cost money, and time is money. So whether it's a mock-up, whether it's performance validation tools, I guess from our standpoint, it's a matter of articulating the value of that, whose means, and we've done a lot of work with developers who IMO for years was, OSB board, Tyvek, siding, and they had a square foot budget number, and that's what they fit in. A number of them we found have had persistent moisture infiltration issues that have led to liability and legal issues. They find an uncontrollable cost. So they finally made the decision, well, we're going to do a little bit more upfront. We're going to use slightly better materials. We're going to do a mock-up. We're going to vet our installers a little bit better. But if I know that, as Jen said, that's a first fix. I have budgets for it, and I know that it's $180,000. as opposed to the uncertainty of mechanicals that don't perform properly, so they have to be replaced, or potential litigation pushed in. So I think from our standpoint, part of it is having them under value down, that you can have uncontrollable runaway costs down the line because you didn't anticipate all the things that are now happening, or some very big proposals that you can actually have on paper and you know what those costs are going to be.
Hi there. Informative. Thanks for that. That was really informative. It made me think about something, and I'm wondering what your thoughts on this is. It seems like if you really pull back, a lot of these issues are happening because of the very free-handed nature in which we, as there's an have come to design and build buildings, where there are an expert for everything who is disconnected from the person. There's a caulking contractor, there's a tape contractor versus a cylinder versus a sealant contractor versus a glazing contractor. I wonder whether you're working in ways in more design build friendly ways where there are integrated teams where people aren't this is a legal issue. I'm just curious what your experience has been, your interest in creating more design build relationships that could have people work together rather than point fingers at each other.
Well, I think you summarized for probably everybody in the room where we'd like to see design and construction go, which is more of an integrated team stakeholder arrangement. And a good example, is the facade in Europe, where just logically they've recognized that it's a lot more, and there's a lot more shared accountability when all of the centralized trades, as you just described, are now centralized in one installer, one company, one ownership. And that can be scaled up, right? That can be scaled from a contractor who's installing and warranting the entire exterior wall to then scaling up to modularized construction, where you've just taken it to the next step. Personally, I think it's an inevitable trend that's going to have to continue, because going the direction that you just described, most people spend 90% of their lives, which is finger circles, been around for years. Typical design bid build says better. Any disconnects along the way that I don't think are getting any. So changing that fundamental delivery process is, it's a legal issue, it's a financing issue, it's a matter of how state extends work together. But in our experience, to the happens doesn't occur. 90% of what we're showing you here, because those issues can be put in place beforehand. So as long as those pieces in place, and we're all of, and I know that George. We live in our own little world. He lives in duct banks and sensors, and I lived in memory sensors. All the it's the important stuff that matters. These, just like projects, are held together by the details. Only is from a team things in those details. So the same approach, to the extent that teams can start to work that way, I think we'll see a lot fewer of these issues that we're talking about.
I think educators have to step up a little bit too and educate each other. One of the best results is from an owner, best sales pitch you can get, or who and sell when they build a building. So you get these new owners coming up that say, I don't need to do commissioning. I got a team of people who are going to pull together and pointing fingers that everybody's going to get pointed at each other because we didn't get together early enough. The general contractor decided that he was going to take every trade on himself, and the coordination, he didn't understand how much coordination it takes to get that work done. So I think as we'll start talking with people, and those kind of horror stories get put before teamwork, that coming together of the team will be. I'd love to see it come together as early in the project as you can. So governors are on board, and we all have a focus going down, learning from each other what the complications are going to be, because we've run into it before, and we know. And I think you're going to see more and more of that coming. But I think it has to come up from the owner. Other than that, they see it as a sales pitch, which I'm not a salesman at all.
Well, and honestly, think of it as a thing here. How historically frequent at that time there enclosure people talk to HVAC people. Sometimes office, all they do is exchange the opposite side of the country and all back and forth. So I think this is somewhat emblematic of the fact that once you start building teams out of knowledge sectors, discovery that we get in the for. I mean, the amount of process is enormous.
Yeah, this has been a great experience for us, getting together and talking about how much outside air I got to bring in condition to make up for what his part of the thing didn't get. We should get to the next
fun,
question.
didn't we?
We had a great time.
Sorry, we got our 2-minute warning, so 1 or 2. I'll stick around until they kick us out, but...
A question on sequence. First, I've seen a lot of problems with control sequences. So this is for operation of sequence. One, for sequence of operation, how are people developing what we call points lists for systems and breaking those points lists down?
Pre-function, when I produce, our documents have point-to-point checklist on them, that also where every point has to be bought out, and then it also has recommended that have to be valved before we do functional testing. So every tested and documented, go to 100% to 50%, and it did that. How much of that happens for real is where the problem comes in. When we do it, we do it all, but when a contractor does it, we believe what until we have to prove it differently.
Sequence 2, your diagramming on that would arguably venture into what we traditionally call means and methods, which designers are traditionally verboten for transgressing. So how do you reconcile the fact that you have now spoken to how the contractor has to teach his trades?
That's probably,
point.
yeah, I mean, that's, I think that's probably the best question to leave as a future challenge. Certainly, I mean, you can, how do you execute on that? Because an architectural firm, it's not your job to tell a general contractor how to put your building together necessarily. But going back much less to the gentleman's comment, we've seen resistance to that, where it might be historically verboten. Now there's more understanding that if teams can sit down, understand the issues, and potentially make decisions collectively, it avoids a lot more problems down the road. So I think that is starting to change a little taboo, where it's not as much as it was for you to sit in a trailer and say, maybe we should think about doing it this way, where there's more open communication to it.
Hi. So I'm speaking from an architect's perspective here. We typically have clients that fall into two categories: who understand commissioning or are very much behind commissioning, have a great in-house group, and those who are kind of begrudgingly pulled along to do it in order to get the lead points, and we'll just do fundamental commissioning, and it's kind of haphazard, and after the fact, and so forth. So I really appreciated your presentation because of the issues and just the simplicity of, the issue so much. I guess I wonder, maybe this isn't so much a question, but I think it would be of tremendous value we have problems communicating the value of commissioning to our clients, why they should be doing it. It's very abstract to some. And I think some of these images were extremely valuable in simply communicating the value of it. And I wonder if there might be a way for you to package that, or to, develop some owner document or something that owners could sort of see as a tangible reason. So it's more of a suggestion. Maybe it's not a textbook, but it's more of sort of a guide with a lot of imagery as opposed to text to kind of illustrate the principle.
Picture
So it's
says
just a thought that
1,000 words. Yep.
A graphic novel on commissioning. You heard it here first. Excellent.
Thank you.
Thank you very much. That was fun.
You guys.